So in Chapter 7, we're going to be really talking about resonance. This is probably the term you learned it as in previous classes. Resonance is also in organic chemistry and in general chemistry known as delocalization of electrons. And then we'll look to see how resonance has its effects on stability, on reactions, and acid strength. Okay, so you'll notice that there's a bunch of problems that I skipped in the middle, 8 and 9. I guess that's not a bunch, but when there's only 20, that's a significant number. And then also we're skipping the last sections of the chapter. Before we go on and talk about delocalization, I would like to give you a better idea about what it means to be a localized bond. Now, there are lots of localized bonds. For example, carbon-carbon single bonds are generally all localized bonds. And if you look at carbon-carbon single bonds, remember there's a carbon here and a carbon here, right? And there's a carbon and a carbon. And on this structure, we have a carbon and carbon. That's a carbon-carbon. Those are carbon-carbon single bonds in several different structures. You notice that the bond length is typically around 151 to 154 picometers. We'll say 151 to 154. Your book talks about bond lengths of about 151, I believe. And that's affected a little bit by hybridization of the carbons that are bonded. But for the most part, that's about where you find most carbon-carbon single bonds. Now, a double bond, for example, a carbon-carbon double bond, I only have one example here. That's 2-butene. Now, a carbon-carbon double bond is significantly shorter, 134 picometers. And again, unless there's delocalization, that's typically what the bond length is. Now, it's shorter because with a carbon-carbon double bond, you're combining a sigma and a pi bond, and so there's more bond strength. And we know in general, as bond strength increases, like this, length will decrease. Shorter bonds tend to be stronger, and longer bonds tend to be weaker. And so we know that a double bond is stronger than a single bond because a single bond is just a sigma bond, and a double bond is a sigma and a pi bond. Now, you'll also notice that carbon-oxygen double bonds are slightly different as well. Here's a carbon-oxygen double bond, and that's about 122 picometers. Now, it's not important that you know the numbers, like the 151 to 154. It's important that you understand the concepts. So again, the concept is it's a sigma and a pi. And because it's a sigma plus pi bond, it's going to be shorter and stronger than a sigma bond. Correspondingly, the carbon-oxygen single bond has a length of 143 picometers. Now, what do you notice about the bond lengths between carbon and carbon and oxygen? Well, if you looked at it closely, what you'll see is that a carbon-carbon single bond is always longer than a carbon-oxygen single bond, and a carbon-carbon double bond is always a little bit longer than a carbon-oxygen single bond. And the simple reason for that is that oxygen, if you think about periodic trends, oxygen is smaller. Is smaller than carbon, and so those bonds are naturally shorter just because the atom is a little bit smaller. Now, another thing to think about in this general trend, O is smaller than carbon. It also makes shorter bonds, and the shorter bonds means they're stronger. Now, let me write a little note here on the side. Stronger bonds equals more stability. So these things affect how molecules will end up reacting. But these, again, are all examples of bond lengths from localized bonds. So now we can talk a little bit more about delocalized bonds. And delocalized bonds, we're referring to resonance. All right, so we can talk about a delocalization, and a good example molecule to start with is acetate ion. I think your book does carbonate ion, but I find that to be a little bit too inorganic for what we've been doing. So I'd like to switch the example that you would find in your textbook, and this will make a good secondary resource. Okay, so acetate, how would we draw it? I'm not going to spend a lot of time on drawing acetate ion, but we'll go ahead and draw it out. It's a methyl group and a carbon, and you've got two oxygens bonded to the carbon. Then you have to decide what to do because the carbon only has 3 bonds, and we also have to have a negative charge on one of the oxygens. So we'll put a double bond on one, and that satisfies the octet for the carbon on the top, the double bond, and the carbon on the right. We'll have to add a pair of electrons to it, and that'll give us a negative charge. Now, there's 2 ways to draw this, and this is what you know from Gen Chem or Chem 3A as resonance structures. So I'm going to go H and C and H. All right, that was a crazy bond. I don't know how that happened. And then C, and then we can put the double bond on this oxygen. And the way you learn resonance structures in Chem 1A or 3A is that if you have more than one way to draw it, then you draw both, you connect them with this resonance arrow. Now, ions in particular, you're supposed to put brackets around, but I'm going to skip that for now, and I'll put the negative charge up here. So, you know, I'm going to skip drawing this every time, but you can just imagine that they're there. They don't really affect any of our discussion. Okay, now looking at these structures, here's some of the stuff you might expect from our discussion of localized bonds. Like you might expect the bond length for a carbon-carbon single bond to be about 154 picometers. You'd expect a carbon-oxygen bond would be 122 picometers. The single bond would be 143 picometers. And we'd also expect something about charge. So in general, your expectations based on this structure is that you would have a carbon double bond oxygen and a carbon single bond oxygens. These would have different lengths. In terms of charge, you would have a neutral and a negative. So those are the things you would expect to have in the structure if you were able to analyze it. And in fact, people are able to analyze the structure of acetate ion in crystallography and look at the actual bond lengths and the charges. And here's what they find. What they find is that both bonds are 127 picometers. It's actually somewhere between a single and double bond. Okay, so the bond length, that's actually what's supposed to be here, right? There's somewhere between a single and a double bond. And the other thing that we find is the charges, both oxygens carry a partial negative charge. And the charge is the same. That is, it carries the same partial negative charge. So the expected bond length would have been 122 for the double bond and 143 picometers for the sigma bond. And we find, again, it's 127, which is somewhere just in between the two. So then the question is, what does it really look like when you have acetate ion? So I'll abbreviate the structure a little bit. I'll say CH3. I have a carbon, I have an oxygen, like this. It is trigonal planar, that it is a sp2 carbon with 120 degrees around the central atom. But what we find is there's a bond, partial bond between these two oxygens, and then a partial negative charge on both both of the oxygens themselves, like that. And this is what we mean by delocalization. We can draw two structures for acetate ion, but the reality is the actual molecule is a hybrid of the two resonance structures, where the bond lengths are averaged together and where the electrons are sort of delocalized or spread, is what that means. The electrons for the bonds and the charges are delocalized over several different atoms. So how do you know when you have delocalization, right? And the first answer, and maybe even the best answer, is when you can draw more than one possible structure for a molecule. So for example, in the acetate ion, we had sort of this anion end that could be drawn like that, with the lone pairs distributed like that with the negative charge. Or you could have had drawn the structure like this, with a double bond on the other oxygen and the negative charge distributed with the lone pairs on the other oxygen. Okay, so that's a possibility. Like when you're drawing the structure, you generally recognize that, oh, I could have drawn it this way, and you get used to that after a while, and that's how you would recognize that you have delocalization, is that you have resonance. But another common way for people to recognize whether or not they have delocalization is look for unhybridized p orbitals on adjacent atoms. That is, there's not a break in between them, but each atom in a series or a sequence has an unhybridized orbital on it. So you can have delocalization, for example, in this molecule, even though you don't think that you can draw it different ways. Right? This is sp2. All of these atoms are sp2. Now, why is it important that they're all sp2? Because remember, when we're talking about a hybridization, right, we're hybridizing as sp2. There's an unhybridized p orbital on that atom as well. And it turns out the electrons delocalize through those p orbitals. That is, remember, electrons are charges, but they're also just electrons, and so if they have an orbital that they can move around into, they can move around into it. And so each one of these atoms, carbon atoms, has a p orbital that can delocalize the electrons. And I'll show you later how you would draw the resonance structures for that particular structure. Now, in our example with acetate ion, it doesn't really matter how you draw it, but if you have a double bond, it's sp2, so for sure it has an unhybridized orbital on it. The carbon's got 3 bonds, right, a double bond on it, so it's also sp2. And then this atom is essentially unhybridized. And so it can participate. These electrons can participate because it has unhybridized p orbitals on it and participate in the delocalization. So you can recognize delocalization by having more than one way to draw the structure. We call them equivalent structures. Or we can also recognize that if I have adjacent atoms, that they are sp2 hybridized or unhybridized in a row, 3 atoms in a row, then there can be delocalization there. So this gives a real quick overview of the resonance model. This is what we've been talking about. And here I'll go back to the book's example of carbonate ion. This is CO3 2-, carbonate. And generally speaking, you can draw its Lewis structure as shown. Again, I didn't put the brackets around, but you might want to put brackets if you feel more comfortable with that. But really, when you draw carbonate, there's 3 different ways that you can draw it. These are known as the resonance contributors. So anytime you draw a resonance structure, each one of those becomes one of the resonance contributors. And then we have the average structure, which we call the hybrid. And in the hybrid, we average the bonds. And then we average the charges. Roughly speaking, on this delta charge is approximately 2/3 of a charge. Now, why do I say it's 2/3 of a charge? There are two negative charges in the structure divided by the number of atoms the structure, the charge is distributed on. So this is the number of atoms that hold the charge in all of the resonance structures, and this is the total charge. Now, it's not that important that you know it's a negative 2/3 charge, but I just wanted you to recognize, sorry for the negative, I just wanted you to recognize that's about how it distributes, okay? So let's talk a little bit about what resonance does to the molecule. First thing that you might recognize is that it spreads the charge. So resonance spreads the charge, and generally speaking, that leads to increased ion stability. Instability of ions like carbonate or acetate ion in solution equates to them wanting to find another charge and participate with that charge as a precipitation reaction or in some other kind of reaction. So increased stability happens because if you spread the charge out and you decrease the total charge magnitude, for example, this is 2/3 of a negative charge instead of a full negative charge, that causes it to be less reactive and causes it to be more stable as a result. Now, the other thing that resonance does is it generally can put charge on or place electrons on atoms with higher electronegativity. And if you can distribute charge to atoms with higher electronegativity, those are the atoms that can handle the negative charge better. So in general, what things that resonance does so far looks like is it causes things to be more stable. Now, the change in bond length, I don't think really has much of an effect on stability, but it is something that resonance causes to happen. That is, the bonds will tend to be a little bit longer than, for example, a double bond, but a little bit shorter than a single bond, so that sort of averages the bond lengths as well. Generally speaking, when we draw those bonds, by the way, I don't know if I mentioned this, we use dashed lines to represent the partial bonds that are created by resonance. So there's a term called resonance stabilization. That's the term associated with the energy of the lowering of the energy of the molecule that has resonance. And that's in contrast to what it would be without any delocalization. So how do you tell how stable a molecule will be? There's a term called resonance stabilization. And resonance stabilization is how much lower in energy a molecule will be because of resonance. So it's the lowering of the energy of a molecule's energy because of resonance or delocalization. And it's really just a hypothetical idea because you can't make the exact molecule without resonance. So you have a molecule with resonance, and then we look at localized bonds and sort of do a comparison between what we think it might have been to what it actually is. And basically what the summary of those kinds of studies are is that the more stable your contributors are, the more resonance stabilization the molecule will have. We'll talk a little bit about what causes contributors to have more stability. I've already mentioned one of the important aspects, that is putting negative charge onto more electronegative atoms. But the other important aspect of resonance stabilization is that the more resonance contributors you have, the more stability you'll get by resonance stabilization. That is, more structures, more resonance structures means more stabilization. Another important, like historically important example of resonance is benzene. Benzene's resonance was predicted by a chemist in Germany named Kekulé, and that's where we get this term Kekulé structures from. That was in the middle 1800s. And in the middle 1800s, he had this dream, and in his dream, he saw a snake. You can think about a snake, right? I don't know if I can do it here. Chasing his own tail. So he's going around in a circle like this. You see, the problem is in benzene, the common thought was that because it was alternating single and double bonds, is that one side should be shorter than the other, but all their experimental results indicated otherwise, that the bonds were all of equivalent length. And so Kekulé had this dream where he thought about the electrons moving in a circle rapidly, i.e. the snake chasing its tail. So we have two resonance structures for benzene where the bonds are alternating between every other carbon. We often draw resonance structures for benzene, or the structure of benzene. You'll see it drawn with a circle in the inside, and that's to represent, in a sense, the snake, the electrons going around the middle of the ring. We find that the bond length is about midway between that of a single and a double bond, again indicating it's a hybrid of those two structures. Now, in order for resonance to exist, one of the criteria is that we have to have adjacent atoms with p orbitals, but those p orbitals have to be able to line up. And for p orbitals to line up, it means that the molecule has to be flat. So if you look at, this is cyclooctatetraene. Cyclooctatetraene. It would be, I guess, 1, 3, 5. I guess it's numbered wrong. 1, 3, 5, 7 cyclooctatetraene. Because the molecule is so large, the bond angles would have to be more than 120 degrees. To be flat, the bond angle would have to be greater than 120. The result is the molecule folds up like is shown on the right. So this is actually going upward. These are up out of the plane. And it turns out cyclooctatetraene doesn't have delocalization because the orbitals can't properly align. When you look at the bond lengths, there's two sets of bond lengths in its crystal structure, one closer to that of the single bond, the 151-ish that we talked about, and the other one closer to that of the double bond. They're a little bit off of those numbers because there's a little bit of resonance or delocalization, but the delocalization is very weak because the molecule can't lay flat for the orbitals to line up. So the next important thing to learn for progressing in organic chemistry is how we draw resonance structures quickly, because we're going to have to draw a lot of them. We actually don't sit around and redraw Lewis structures over and over and over again. And in fact, you get used to seeing patterns in structures that produce resonance structures. And we use electron arrows. Remember we talked about electron arrows in the reaction mechanisms of the alkenes and the alkynes. And we use the electron arrow. We refer to one end of the electron arrow as the tail and the other end is as the head. That's the arrow end. And we always start, when we used curved arrows in drawing resonance structures, we always start with the electrons on always start with the arrow on electrons. Now, the electrons can be either lone pairs or they can be bonds. And it always ends on another atom or another bond. And I'll talk about some of the other restrictions on this, but basically, if I was going to draw the resonance structure for this molecule, I would do that. That is, I can move that pair of electrons from the double bond and put them into between two other carbons and create another double bond. Now, I drew this hydrogen here for the purposes of illustrating that this carbon is sp2 hybridized. It only has two groups or three groups on it, and it's a carbocation, so it's sp2. When I move the electron pair like I show here, I can redraw one of its resonance structures. In this case, there is only one other. That is, I can redraw it like this, and then this hydrogen is here. Now, you'll notice there's also a hydrogen over here. So when that pair of electrons moved, I had to pull it away from this carbon, so now the positive charge is up here. Okay, so we always start with the electrons on, always start with the arrow on a pair of electrons, and we move to either the position of a bond or an atom. Another way to do it is like this. Here's the next example. I can move this here. Now you notice these atoms, which I'll highlight in a little bit of a different color, these atoms all participate in resonance because they're sp2 hybridized. And when I do that, I don't want to violate the octet rule, so I'm going to move these electrons out here. Now when we do that, we have to keep track of formal charges. Right now it's neutral, but then I'll have an oxygen that looks like this. Right? There were two electrons here because it was double bonded. And so this will have a negative charge. There'll be a double bond between the nitrogen and the carbon, and a positive charge on the nitrogen like that. And these would be the resonance structures. But again, I started the arrow on a pair of electrons, that's here. And when I went to move it, there was already an octet at this carbon, so what I was able to do is, because there's a pi bond here, move these electrons out and place them onto that oxygen. This is a significant resonance contributor to the structure, simply because I can put the negative charge onto the more electronegative oxygen. Some rules, and there are actually very few rules when drawing resonance structures. One is, don't, if you can, try to avoid breaking single bonds. There will be times in the more advanced organic chemistry class when we do mechanisms where single bonds get broken, but in resonance, we avoid breaking any single bonds. If you, for example, put an arrow starting at this sigma bond, when you move the electrons, what you essentially do is you break that bond, and you would end up with two different things. And in resonance structures, you're supposed to move electrons but not change the overall structure of the molecule. Okay? The other thing that you need to avoid doing is violating the octet rule, especially for second period elements. Okay, so how do I know I can't do this? And part of the way you know is you draw what's missing. Or in your head, you know there's two hydrogens there. So if I move this pair of electrons in like I did, what I would have is I would have this. And that would have 5 bonds, and it would violate the octet rule. So we can't do that, and we can't do that. Those are the two primary restrictions on resonance structures that you can't do. So let's take a look at these two structures and determine which one can have resonance. Okay, and then we'll draw the resonance structures. And then we'll draw the hybrid based off of the resonance structures that we end up drawing. Okay. Look at molecule A. In molecule A, I have, in terms of hybridization, I have sp2, sp2, and sp2. So I can have resonance in that molecule. Look at molecule B. This is sp2, this is sp2, and this is sp2. And what we notice right away is in between the sp2s, I have this sp3. Okay, so we can draw a resonance structure for structure A. I can just simply move this electron pair and put it to there. And I want you to pause the video and draw the other resonance structure. So you should have ended up with something that looked like that, where the double bond has moved over. And if you wanted to, you could have also drawn a little arrow in between to indicate that there are resonance structures of each other. Now what I want you to do is pause the video, draw the resonance hybrid, and use the delta notation to indicate where the charges are. All right? So that's what your hybrid should look like. I left the atom labels off, but that's what your hybrid should look like. Should have dashed lines, and on either ends of the dashed lines we have a positive charge distributed. The positive charge never distributes in this molecule onto this carbon. That one always remains neutral. So let's talk a little bit why B can't be drawn. You couldn't draw a resonance structure for B. And the answer is simply this. It's sp3, it's got 2 hydrogens on it. If I try to delocalize these electrons towards that positive charge, and generally electrons like to move towards a positive charge, I can't, because in order to do that, if I drew that part of the structure out again, I'd have a carbon that looked like that, and this would be 5 bonds. So having an sp3 carbon in between carbons disrupts any possibility of delocalization. Let's draw some, let's determine which of these we can draw resonance structures for, and then we'll draw the resonance hybrids for each. So go ahead for C. I would like you to identify whether or not it can do delocalization, and then do D and E as well. And we come back, I'll have highlighted the atoms that are allowing resonance or not allowing resonance. So as it turns out, all these structures have a form of resonance. I'll show you, D is an oddball. I'll show you that one as well. But it's something that you'll see quite frequently when you're drawing mechanisms or when you're looking for a resonance. The first thing to recognize is that if you have a lone pair, and this is what we talked about before, lone pairs can participate in resonance because on those atoms they're essentially unhybridized, or even though they're sp3 hybridized, they have a pair of electrons on them. And C and D illustrate something known as an allylic resonance pattern. It's something that comes up quite often. Now, allylic, if you remember what allylic means, this is the allylic carbon. And oftentimes, when you have a carbocation or a carbanion, either one, you can have an allylic resonance pattern. So here's what I have, a lone pair, and this lone pair can go to here, and then this can go to here, like this. So again, the presence of a double bond allows me to push the electrons for the nitrogen to this carbon, and then I can, instead of violating the octet rule, because that would violate the octet rule at that point, I can move this pair out and put the electrons onto that carbon. So that becomes this. And then this is an sp3 carbon, so the pattern will stop at that point there. So I end up getting H2 positive and negative. Now we'll talk about stabilities of contributors in a little bit, but this is a possible resonance contributor based on this allylic resonance pattern. Here's another one on E. Let's take a look at E. E can go like this, and then again, using this allylic pattern, I can move these electrons onto this carbon here. That gives me this. That as my structure. Oh, and there's a positive charge on the oxygen. Okay. Now, how is it that D can have resonance? D can have resonance in the sense that this atom is sp2 and only has 6 electrons. So really, the nitrogen can donate a pair of electrons like this and produce this. Like that. So it's similar to the allylic pattern, except for I don't have a pair of electrons, a pi bond to push out of the way. Okay, so this is an allylic resonance pattern, and that's one of the ones that you need to become familiar with and how to draw. Here is a molecule. It's called pyrrole, and pyrrole also has allylic resonance pattern in its structure. And what I did to make this go a little bit faster is I drew all the rings in to give me the resonance structures to help speed this up for us a little bit. We have a nitrogen, and you can push the electrons here, and then these electrons will go like that. Okay, so that gives me, in the next molecule, gives me this. Whether I draw the bond on the outside or the inside doesn't matter. And it doesn't really matter if I went to the left initially or if I had gone this way. I'll end up with the same resonance structures going either way. And if you want to check that out for yourself, feel free to do that. But again, it's an allylic resonance pattern. So now, notice what happens. I can go like this, move this pair, and then this pair can move to here. So what's going to end up happening is I'll end up with this. I have a positive charge here, and I can put the negative charge here, like that. So go ahead and draw the next resonance structures. I'll pause the video, or you should pause the video and try to do those, and then check to see how your answers compare. So this is the next resonance structure. You notice that I took and let me get the little pointer out here. I drew the arrows here, and then I moved the double bond to this position, and I have a lone pair here. I'll do this one more time, and then I can push this pair back to here, and then this will go back onto this oxygen, or that carbon. So there's the next structure, and you'll notice again I push these electrons in the same direction. And since I started counterclockwise, I generally tell students, hey, just stick with that pattern, keep going counterclockwise until you run out of resonance structures. So I moved this pair into here, and then I ended up having this particular structure. Now, the last structure that you can draw will go something like this. Oops, sorry, didn't mean to do that. The last structure we have goes like this. That is, we can take this pair of electrons and move it here, then this electron will move here. That actually takes us back to our original structure. And so this is a cyclic compound, and very often with cyclic compounds, you will draw resonance structures in one direction, that is counterclockwise or clockwise, and eventually you end up back at the original structure. Now, let's think about what this resonance hybrid looks like, because this one's a little bit different than some of the other ones we looked at. It's definitely a lot more complicated. So if I'm drawing a 5-membered ring with a nitrogen, I've got a nitrogen in the middle like that, and I got a CH3 coming off of this guy here. Right? Where is the negative charge in the structure. Well, if you look at the negative charge in the structure, right, you had it here. This was a negative here. You had it here. Then you had it here. And you had it here. Right? And you had it on all of the 4 carbons. So the bonds all delocalize. There's a double and single bond combination for every single atom that's bonded, and then there's a partial negative charge on all of the carbons. Then the question is, what about the positive charge? And it turns out the positive charge is always on the nitrogen. So I have a partial positive charge on the nitrogen and partial, negative charges on all the carbons. I put positive, sorry. Like that. And that's what the delocalization causes to happen in parole. So let's talk a little bit about predicting stability. So I have a structure where I take the nitrogen and I push the electrons to the carbon like this, another allylic pattern. I end up with a positive and I have a negative. Okay? In general, and we know that nitrogen is more electronegative than carbon. We know that based on periodic trends. And so putting the positive charge on the nitrogen versus the oxygen, right, or the more positive charge on the oxygen, cause it to be not as stable. So we would predict that the stability of the resonance structure over here is that it is less stable than the one that we drew initially. Remember, this structure that we drew on the left, this is also one of the resonance structures. So contributor stability also affects what the structure of a molecule ends up looking like, the structure of an ion ends up looking like. I've drawn 2 resonance contributors for the same molecule. You can draw the resonance structures by pushing the electrons. Again, it's one of those allylic patterns, even though it involves an oxygen, but an allylic pattern pushing electrons. To go backwards, you could push the electrons this way, get back to the original molecule. But you'll notice that in this particular structure, just like in the previous structure, I put the negative charge on one atom, and this is a negative charge on the more electronegative atom. The result is, because it's on the more electronegative atom, we would predict that this would be more stable. The one on the right, the structure on the right would be more stable. And this one is less stable. So when we're thinking about resonance, we're moved away a little bit from the idea that that all the resonance structures are equivalent. Now some resonance structures are a little bit more important than others. And when you think about what the molecule will actually look like, the hybrid, it's going to look more like the more stable contributor. Now, if you look at the electrostatic potential map, we haven't looked at these in a long time, but remember, this means negative charge. And this means positive, and this is neutral. You'll notice what's happened in this structure on the right. There's more negative charge over here on the oxygen than there is in this region. Now, it is distributed between the 2 atoms, but most of the negative charge is on the oxygen. So the resonance contributor stability helps us to predict where we would find charges on the molecule. So contributor stability also affects what the structure of a molecule ends up looking like, the structure of an ion ends up looking like. I've drawn 2 resonance contributors for the same molecule. You can draw the resonance structures by pushing the electrons. Again, it's one of those allylic patterns, even though it involves an oxygen, but an allylic pattern pushing electrons. To go backwards, you could push the electrons this way, get back to the original molecule. But you'll notice that in this particular structure, just like in the previous structure, I put the negative charge on one atom, and this is a negative charge on the more electronegative atom. The result is, because it's on the more electronegative atom, we would predict that this would be more stable. The one on the right, the structure on the right would be more stable. And this one is less stable. So when we're thinking about resonance, we're moved away a little bit from the idea that that all the resonance structures are equivalent. Now some resonance structures are a little bit more important than others. And when you think about what the molecule will actually look like, the hybrid, it's going to look more like the more stable contributor. Now, if you look at the electrostatic potential map, we haven't looked at these in a long time, but remember, this means negative charge. And this means positive, and this is neutral. You'll notice what's happened in this structure on the right. There's more negative charge over here on the oxygen than there is in this region. Now, it is distributed between the two atoms, but most of the negative charge is on the oxygen. So the resonance contributor stability helps us to predict where we would find charges on the molecule. So the last thing I want to cover in terms of stability is to talk a little bit about octets and resonance and stability. When you have a structure like the one shown on the left with the nitrogen, what it can actually do is it can actually donate a pair of electrons. And then it takes on the positive charge. And we know that putting positive charge on a more electronegative atom is not necessarily beneficial to the molecule. But here, what we have is a carbocation. And carbocations, hopefully you've picked up from the earlier lectures, carbocations are very unstable because they only have 6 electrons. They don't satisfy the octet rule. We have a hydrogen here, but that only gives this 6 electrons, and it turns out when you do something like this, right, we have a hydrogen here, I have my 4 bonds, and so this satisfies the octet rule. The result is this molecule on the right, the molecule as drawn on the right, this is more stable than the one shown on the left. So I thought it would be helpful to sort of summarize some of the things we talked about in terms of resonance structures and stability, and so I'll put those on a separate slide. First of all, you need to recognize some important patterns in resonance structures. One is this. That's the allylic pattern. We see this one all the time, and so I typically will just teach this one separately all by itself like I did in this lecture. Another important thing to recognize is how to use the arrows. The arrows start on electrons, and those electrons can be bonds, and oftentimes they're lone pairs. And they always end on bonds or atoms. And that's the use of those arrows in general, it turns out. In mechanisms, they'll often be the same kinds of actions with the arrows. The third thing is we try not to, and I don't even say try not to, for resonance structures, don't break sigma bonds. And also, don't violate the octet rule. Don't exceed an octet. On second period elements. know that we have potential for resonance. Oh, sorry, that's 4. Whoa. We have a potential for resonance when, 1, we can draw more than one equivalent structure. And with one exception, I'll talk about that in a second, you have adjacent p orbitals. And that has to do with hybridization, numbers of bonds. And we also talked about lone pairs. And in the earlier part, I said is when you have 3, and that's most of the cases. But you can also have it with the lone pair and a vacant orbital. So you can have resonance of a sorts when you draw structures like that. So that is also a possibility. Now, when we're looking at stability caused by resonance, there's a couple of things that we end up looking at. One is we look at the number of contributors. And more is more stable. We would say higher stability, with an understanding that higher stability actually means lower energy, right? It becomes more stable as a result of having more contributors. One of the other aspects when we characterize resonance contributors and we try to determine stability is we look at charges. And in general, we want more negative charge on more electronegative atoms. But we also want to make sure we satisfy the octet rule. So things like carbocations tend to be exceptionally unstable. And in fact, in determining contributor stability, octet rule is probably the first thing that we look at, and presence of carbocations is generally one of those things that triggers in our head that that's an unstable contributor. Another aspect is that in order for resonance to take place, the molecule has to be flat. The p orbitals, so I think the criteria maybe is most concisely put is p orbitals have to align. And I'll just say must line up. And in terms of structure, what we see in the structure of a compound that allows that to happen is that the molecule is flat. This becomes an important aspect of the next chapter when we look at something called aromaticity. And aromaticity is sort of an extended version of resonance, but the stability that's gotten from aromaticity is just a lot bigger. So it gets a whole chapter in its own. But when we look at those structures, one of the criteria is those molecules are all flat that have resonance stabilization in the next chapter. So we have to have molecules that are flat. That's why we stressed early on when you're looking at structures around carbon-carbon double bonds that all the molecules, all the atoms in that part of the molecule are in the same plane. That allows us to line up those p orbitals. That's the flatness of the molecule. And sort of lastly, another subsection, sorry, when I draw a little thing like this, is some of the terminology that goes along with resonance and resonance structures. So we have contributors. Those are the individual drawings, which essentially show localized bonds. Okay, and then we have many contributors, which then allows us to make a hybrid. So contributors are drawn with solid bonds, right, and positives and negative charges. Hybrids are drawn with the dashed bonds to indicate the delocalization of the electrons, and we talked about partial positives and partial negatives. Now, some hybrids will also have full positives and full negatives if that charge remains the same in all the resonance contributors, but if it delocalizes at all, we use partial negatives and partial positives. In the hybrid, we talk about the number of structures, and we talk about resonance stabilization. And resonance stabilization is the stabilization of the molecule versus the hypothetical molecule without delocalization. Okay, so resonance stabilization is the lowering of the energy of the molecule. It's hypothetical based on the idea that we could have the molecule and have localized bonds in it, and then we compare it to the molecule when we allow delocalization to take place. So what I'd like to do next is talk about the effects that resonance have on both the structures, organic compounds, and also it has on the properties. So what I'd like to do now is talk about how delocalization or resonance affects the properties of organic compounds. This includes acids, which are made stronger by delocalizations, and bases, which are made weaker. So when I say an acid is stronger, really what will be referring to is its pKa. And its pKa will be lower because of delocalization and the distribution of the charge that's created when the proton leaves. Now, bases, when I say bases are weaker, what exactly does that mean? What that actually means is it means the same thing, actually. The pKa is also lower. But when I'm talking about pKa's of bases, for example, ammonia. If I were to say ammonia became weaker because of delocalization, really what I'm saying is NH4 plus is a stronger acid. Because if a base is weaker, its conjugate acid becomes stronger. So again, it's still the pKa is lowering, but we're talking about the ability of the base to accept a proton in a reaction. That actually gets weakened by delocalizations. And finally, we'll talk a little bit about carbocations, because we talked about electron donation effects of alkyl groups and how that stabilizes carbocations. But we also need to discuss how resonance affects stability. And then the last big category of things to talk about is how molecules with conjugation or with resonance, and we'll talk about that in specific as we get there, are stabilized, and that causes them to behave differently, to have different properties, and also has them react a little bit differently as well. Because of the delocalization of charge, we can end up with some relatively unexpected products, and we'll go through and show how you can expect what those things could be. So let's talk a little bit about resonance and acidity. When I have acetic acid and I react it with water, it produces hydronium. This is the hydronium. The strength of the acid is determined by its equilibrium constant, or Ka value. Ka is going to be the concentration of products over the reactants in the general form. And the more product that I form, the bigger the Ka value is. Now, the ability for an acid to dissociate is directly related to the anion's stability. if the anion is more stable, then it's easier for the acid to dissociate in solution to form that ion. In other words, increasing anion stability increases the Ka and then lowers the pKa value. So what is it that gives this example, acetic acid, its strength? That is, why is the pKa of acetic acid what it is? And really what it boils down to, as we've looked at before, is delocalization. We drew acetic acid earlier. That was our first example with resonance. And we know in the hybrid, I have delocalization of the charge onto two atoms. So I have a partial negative there and a partial negative there. By lowering the charge density, is usually what I like to say, but lower charge density, lower charge density allows the proton, which is positively charged, to leave more easily. Now, there are a couple of effects going on here, so I sort of wanted to go back and review a little bit. Okay, so when we're talking about the acidity of a compound, for example, alkanes in general, pKa's are around 50 to 60, depends on where you read, but it varies between about 50 and 60. In other words, this hydrogen can't come off because this anion is exceptionally unstable. Okay, so the hydrogen ion can't pull away because the anion is very unstable. Its pKa, in other words, is very high. Okay, now when we look at ethanol, this is ethanol. In all alcohols, their pKa's fall in the 15 to 16 range. That's much, much lower, right? So this is a much stronger acid. And the effect that we're seeing here has to do with electronegativity. So this comes directly out of chapter 2 stuff, right? If I have a more electronegative atom, and for example, I make this ion, it's called the ethoxide ion. When I make ethoxide, this can happen much more easily than on an alkane, simply because the oxygen's electronegativity allows it to carry charge more easily. And then, we don't really think about this, but a pKa of 15 versus a pKa of 60, that's 45 pKa units. So it's 10 to the 45 times stronger as an acid, as an alkane. Now, again, that's due to the electronegativity of the oxygen. Now, when you look at acetic acid, the acetic acid is, again, about 10 to the 10 times stronger. So putting that in like numerical values, right, roughly 10 billion times stronger than ethanol. So this is acetic acid again. That's because when you have acetic acid, you can delocalize that negative charge. So I have delocalization or resonance, right, which allows the charge to distribute that causes the acid to be stronger. So really there are two main effects that we see in a lot of acids that make them stronger. One is simply electronegativity. You have a more electronegative atom, that acid will be stronger. And then we also have delocalization, which also contributes to making the acid much stronger. If you look at phenols, which are alcohols, this is a phenol. Right. Phenols are stronger acids even than, like, for example, alcohols. They're not normal alcohols. Even though a phenol is an alcohol, it has the ability to delocalize its electrons into the benzene ring that increases stability. The same thing is true for the protonated form of a molecule called aniline. This ion is known as the anilinium ion. I don't think you really need to remember that. But this is what is drawn on the screen. But that's the protonated form of aniline. It's also relatively strong. It's stronger than phenol simply because the electron pair is more easily donated to the ring. Okay, so let's look a little bit at the resonance structures for these molecules to see how the electrons delocalize into the ring. So here's aniline. And when aniline acts as a base, right, what happens is this pair of electrons will pick up a hydrogen, and those will go back to the oxygen, and you'll have, I forgot to draw this over here, hydroxide ion. Okay? Now, acids are made stronger, but bases are made weaker for the same reason. If I were to redraw this resonance structure, I could draw it like this. And so I drew some skeletons down here so we could draw these quickly. I'd have a lone pair here, a double bond, and a positive charge, like that. Okay? Now, this is delocalization into the ring, is what we would say, and it uses the allylic resonance pattern that we drew before. The next resonance structure, again, going in the same direction that we started, would do this. Positive charge here, right, and a pair of electrons here like this, and then this double bond hasn't moved yet. My negative charge is with my lone pair, and then again in the allylic pattern I can bring this pair in and drop that pair there. It'd be like that. Again, I have a double bond here, I have a double bond here, going based off the previous structure. Now my double bond is there. My negative charge is like this. And then the next structure goes like this. And then these electrons can return back to the nitrogen, and then I'll end up with this pattern that looks like this. Now you notice the only difference between these two is the positions of the double bond. And using Kekulé's idea, you can show also that the bonds can all rotate over like this. And this is back to the original structure. Okay, so those are all the resonance structures that are available to aniline. Now let's think about what this does. This pair of electrons, which I'll highlight this way, this pair of electrons is involved in resonance, and it's involved in the acid-base reaction for aniline. When it's doing one, it can't do the other. In other words, you can either contribute to the ring, or you can pick up the proton and become like this, but this is the same pair of electrons like that. So you can either do one or the other. And when you have a choice, in essence, both are going to be going on all the time. And as a result, the electrons on the nitrogen are partially occupied by their time in their ring. You notice in all of these structures, those electrons are occupied the whole time. The only time it isn't is when it returns back to this form. Okay? So since some of the time the electrons aren't available for acting as a base, then the base has become weaker. That is, occupying the lone pair of the aniline by putting it into the ring makes the base weaker. So what does that mean? The weaker base means a stronger conjugate acid, and the stronger conjugate acid, right, means the pKa is lower. You can do the same drawings by substituting for the nitrogen. You could substitute an oxygen, and you would essentially be doing the same work for phenol. And what you would see in phenol, and I'll draw that here now, is once phenol becomes a phenoxide ion, what's the name of this guy, it can also follow this allylic lone pair pattern and produce a series of resonance structures. That stabilizes the negative charge on the oxygen, distributes it into the ring, and makes it less available for picking the hydrogen back up. In other words, because it's able to distribute charge into its ring, it lowers its pKa and becomes stronger. So anytime you see an atom on a ring that's acting in a reaction as an acid or base, the pKa is always going to be lower. So you hopefully remember in discussing carbocation stability that carbocation stability follows the trend of tertiary being more stable than secondary being more stable than primary. That is, if I have a carbocation that looks like that, it's going to be more stable than a carbocation that looks like that. This would be a primary, and this would be a tertiary, and a secondary would be the one in between. Now, when we say stability, too, I want to make sure we understand that means lower in energy. So tertiary carbocations are lower in energy than primary carbocations by a significant amount. Now, it turns out resonance or delocalization has an effect on the stability of carbocations as well. So here we have a tertiary allylic carbocation, and then we have secondary, and then we have primary. When we talk about delocalization in these, what pattern we're looking at is this one here. Again, those are all sp2 hybridized. And then I end up with a structure that looks like this. And the positive charge is now in the primary, but the hybrid looks like, oops, I drew two, has a dashed line like this, has a positive charge here and a partial positive charge there. And by delocalizing the charge on two atoms instead of one, you gain a great deal of stability. Now, the least stable of these is the primary allylic carbocation. That's this one. And it turns out in terms of stability, it's about the same as a tertiary. So a tertiary this would be a tertiary like this one here. Tertiary, secondary, and then primary. This. So the fact that you have resonance or delocalization for that charge makes it a lot more stable than if you don't. That is, it puts it on the scale of the secondary or tertiary carbocation. This is an interesting carbocation. This was actually one of the first ones that was isolated. It was first carbocation that was stable enough to be isolated and studied on its own. They just got it to be really cold and they could trap this structure. But this particular carbocation on this end, the one I had underlined, is exceptionally stable because not only does the charge distribute to a double bond, for example, like this, it also has three benzene rings or phenyl groups to distribute into. So this benzylic, it's called a benzylic type of carbocation, is exceptionally stable, and you can delocalize into multiple rings in this particular structure. Let me just make a note. This is the one that's really important for us. This is benzylic. Okay, it's the carbon adjacent to the benzene ring. Those are the carbocations we'll see a lot in this class. Now, charge stabilization has a big effect on, or delocalization has a big effect on the distribution of the electrons in a structure. If you'll notice, this is the electrostatic potential map for this carbocation, and this is the electrostatic potential map for this one. And the blue charge is the positive charge. Now, this is localized. There's no sp2 carbons adjacent to the carbon that we've drawn here. And the result is all the charge gets localized onto this group. Now, that's this guy here. Okay. And the atom, this is the atom in the ring, I think, or the hydrogen on the atom in the ring. Now here, right, because I have delocalization, the charge goes throughout the ring. You'll notice that this portion of the ring is not as green as it is here. And that's a result of the positive charge being spread through all the atoms. Now, charge stabilization works for anions as well. So I have a carbanion here, and charge stabilization for anions follows the same allylic pattern that we've looked at before. And then you can draw the delocalization like that. Again, you would have a double bond here, lone pair here, negative charge, like this. And then we're going to push it one more time, put the electrons here, and then we'll have a pattern that looks like this. And then we'll do it one more time. And then so I would push those electrons, and then I would have this. The negative charge here, and then I can push these into here, and these would go up like this. And that would give me my original structure, almost. I'll show you in a second. Gives you this. And then again, following that benzene ring pattern, push these around like that, and that would get me back to my original molecule. Now, when you have delocalization that occurs like this, we can also draw a hybrid, and this is an important concept, I think, to get across. The hybrid would have a delocalized bond all the way around the inside. I'll have the CH2 up here. And there would be a partial bond here too, because you notice part of the time there's a partial bond all the way through on that carbon. I would have a partial negative charge here for sure, because that's where it started. But then I have partial negative charges spread throughout the ring. And those locations would be every other carbon. So it's not on every atom that charge gets distributed. And the jumping of the charges, you notice every other carbon, like 1, 2, 3. Let me get the highlighter out here, or the pointer out. 1, 2, 3, 1, 2, 3, 1, 2, 3. Going every other carbon. That's a sort of a feature that we see in charge delocalization, either positive or negative in lots of structures. So one more aspect that I'd like to cover about structure and stability is the idea of conjugation. And here I have 1,3-cyclohexadiene and I have 1,4-cyclohexadiene. And it turns out 1,3-cyclohexadiene is more stable than 1,4. And the reason for the stability is a term that we call conjugation. That is, we have continuously connected sp2 carbons. Here, what I have is sp3. There's 2 hydrogens there, and there's also 2 hydrogens here. And that is termed to break the conjugation of the ring, or of the double bonds. So conjugation allows for stability because the conjugation, the resonance of those structures is perhaps not easily seen. Okay, so what I'm going to do is show you how to draw conjugated polyenes as structures with more than one double bond, and show how their resonance contributes to their stability. So it's a little bit complicated. So in this diagram, I took this actually from the book's notes, but I'll redraw some of this in perhaps a simpler form. I'm going to just draw it like this. So this is also a diene like that. Now, I could draw resonance structures for this by drawing this bond going this way and this one going that way. So that would give me a resonance structure that looks like this. Then I'd have a lone pair of electrons here and a negative charge, and I have a positive charge over here. Or I could use in a different color, and I'll just do what the book is doing, just so you can see how they're doing it. Or I can make it go the other way. Okay, so I can shift the electrons in the other direction. What that causes to happen is for there to be another resonance structure that looks like this. Now, what did that do? Because you'll notice that I have negative charge here, positive charge here, I have a positive charge here, negative charge. And separating charges generally causes instability. And in fact, you've created a carbocation here. So this is only 6 electrons. Oops. And we talked about this before, that not having an octet is one of those things that makes a resonance contributor less stable. But it turns out still, because the delocalization allows the charge of the bonds to distribute like this, okay, right, it causes them to be more stable. So, right, there are different resonance contributors, but not all the contributors are as important. But still, having those contributors lends to stability to the molecule. Now, charge stabilization has an effect in chemical reactions. Here's an electrophilic addition reaction. We looked at these reactions in previous chapters. Go back to my red pen. And in those particular reactions, I have, for example, HBr. That pi bond breaks and attacks, and the bromide ion gets formed. When you do that, there's actually two carbocations that are possible, so there's two possible products. That is, one with the bromine in this position, or one with the bromine in this position. Now, the carbocations that formed, we know a positive charge, right, in the intermediate had to have the positive charge there. And the same is true for this one. But it turns out the only product that we see out of this reaction is this one here. And the reason for that is, and generally speaking, you'll see this a lot, the reason for that is that particular intermediate is a lot more stable than the other one. So let's look at the possible intermediates. Right? Here's the intermediate with the positive charge next to the ring. In that case, you can have delocalization, and I'm not going to draw all the structures, but you can have delocalization and distribute that charge into the ring. And this one will go like this, and again, you're going to have positive charge distributed to this carbon and double bond here. So you can do that and draw all the resonance structures. What you'll find is, and this is going to be the hybrid, so I'm not going to draw them all. Is that there'll be a partial double bond here, and then all throughout the ring. Now you're going to have a partial positive charge here, and then following that allylic pattern that we looked at before, every third atom will have a partial positive charge. So I'll have one here, here, and here, like that. And that's what we see in that particular structure for its hybrid. The ability to distribute that charge makes this intermediate much more stable. Now, the other intermediate in the reaction would have been this one, and I'm not going to spend a lot of time on him. The other intermediate would have been this. Oh, sorry, let me just draw the double bonds. Like that. And you'll notice that this is isolated from the benzene ring. And so this is sp3, and it doesn't have an open p orbital, so it can't delocalize that charge. That charge is actually fixed in place. So the result is having this positive charge adjacent to the ring allows for delocalization, and then having this one split away from the ring by an sp3 carbon prohibits any delocalization and causes that particular carbocation to be slower forming, and so we end up with the other product. So what I want to do next is talk about reactions of dienes. And on the top I have an isolated diene, and the bottom I have a conjugated. Isolated and conjugated because on the top molecule there's an sp3 carbon which breaks the conjugation between the two double bonds. Conjugated below because they're continuously sp2 hybridized carbons adjacent to each other. When I add one equivalent of HBr, that is 1 mole of HBr for every mole of reactant, the isolated diene gives me the product that produces the most stable intermediate in the reaction. Now, you have to imagine there's two possible intermediates, one with a positive charge that forms here, and one with a positive charge that forms here. So in the intermediates, I have two choices of the double bonds to react with in the electrophilic reaction. And the one that gives me the more substituted double bond will give me the main product of my reaction. For sure, there'll be some of the minor product present, but the major product will be the one that I've shown here, where the bromine is attached to the carbon where the carbocation was formed. Now, if I add a second equivalent of HBr, then what ends up happening is I'll end up adding HBr to both positions. I'll have a Br here as well as a Br here. So I can add to both double bonds separately, but the one that reacts the most quickly will be the one that produces the more stable carbocation. That typically is your major product if you only add the one equivalent. Now let's look at the conjugated diene. The conjugated diene is a little bit more complicated. For sure you get what you might expect to get, that is, I added to that double bond because that's a secondary carbocation. This is known as the direct addition product. Or the 1,2 addition. It's called the 1,2. It's not because of the IUPAC numbering. It's because it's the first two carbons in a set of conjugated double bonds. So it's the first two carbons. So it's 1 and 2. Now, when I'm looking at the other product, you'll notice that the addition happened as 1 and 4. So this is known as conjugate addition or conjugated addition. Or 1,4 addition. So let's talk about a little bit about how you get these two different products. This is for the same one equivalent of HBr. So we'll look at the two products, we'll draw their intermediates, and talk about how they form. So first of all, in the mechanism, I have HBr, and it is attacked by the double bond, by the pi bond, of the carbons between carbons 1 and 2. So I end up with this as my intermediate. The hydrogen's added, I'll draw it off like that. All right, and then what happens is that the bromine comes in, the bromide, right? That's produced from that first step. That comes in. It can do that, and that would give me that as my product. Now, turns out that there's a resonance structure as well. So I can go like this, and I'll end up with, by moving that pair of electrons, this carbocation. The hydrogen I added is still down over here. That's still the same place. But what's happened is the electrons have moved because of resonance. When it does that, then the bromide, again, formed in that first step, can attack over here, and that's what gives us this product. So this kind of product occurs any time that you have resonance. That is, if you have resonance, then you can add a bromine to that particular, to two different positions because of the delocalization of the positive charge. Now, in general, in isolated dienes and in conjugated dienes, the double bond that reacts is the one that gives you the most stable initial carbocation. Or sorry, the most stable carbocation. So, for example, if I were to form carbocations from this first molecule, the most stable carbocation would be this one versus this one. So this is the intermediate that will lead to your product because in this case of this isolated diene, that's the carbocation that is the most stable. Same could be said about this molecule. If I were to add HBr to this, I could break the bond like this, or I could break it like that. But the carbocations that are formed are significantly different in that this is a tertiary carbocation, and this other one would be a secondary carbocation. The positive charge being either here or being at the upper position if the hydrogen adds on the other. But these are both secondary. This is tertiary. So when you have one equivalent of HBr, the most likely product will come from this as the intermediate. the next two examples are examples of conjugated dienes. So if the HBr were attacked by that double bond, then the intermediate for that reaction would be this one. Now, you might be wondering, why isn't it this one? And I'll cross it out when I'm done here in a second. Why not doing it this way? Oh, sorry, positive, intermediate, positive charge here. And the reason for that is by adding it in that fashion, this is an sp3 carbon. And that sp3 carbon doesn't allow for the delocalization of that charge, so it's certainly not the most stable carbocation. So by having this charge here, that allows for delocalization. And then by having this sp3 carbon here, that stops the delocalization. So this is the intermediate that leads to the formation of your major product. I should point out one other thing as well. The other product that you would get from this particular structure is following that resonance arrow. You could have also a product in which the carbocation is distributed to that point, and then the nucleophile is added at that point. It's important to point out that this is a combination of a tertiary and a secondary carbocation, and those are particularly stable. Now, if you're looking at this lower molecule, and I put HBr in here, and you're thinking about which carbon is going to be the one to initially react, turns out the most likely one is this one. And when you do that, you'll have a positive charge here that can delocalize to the double bond, right? And then by resonance, that delocalization would give me that. Is a combination of a primary and a tertiary carbocation. The result is that you could expect to have products that are attached either, where the nucleophile is attached there or attached at that point there. Okay, so those are the things that you'll be looking at and determining what products you get if you have two double bonds. If they're isolated, the most stable carbocation will give you your product. And if it's a conjugated situation, then what you have to do is you have to look at both the most stable carbocation, but you also have to look at the delocalization and how that affects where the charge appears in the product, or in the intermediate, which then leads to the product.